All right, let's dive right into this explainer. Today, we're taking a journey all the way down to the atomic level to really understand how forensic science delivers absolute certainty. We're unpacking the incredibly high-stakes world of forensic chemistry to explore the ultimate molecular detective. We're talking about a machine that can take the tiniest, most anonymous speck of evidence and completely decode its deepest secrets. It's a pretty wild ride involving intense heat, deep vacuums, and electromagnetic shattering. So let's get into it. Picture this. You're standing in a clandestine apartment laboratory. On the table right in front of you is a simple dusting of white powder. To the naked human eye, it's totally anonymous, cryptic even. I mean, it could literally be baking salts, or it could be a lethal dose of a synthetic narcotic. Human eyes are easily fooled, and as we know, human eyewitnesses can absolutely fail on the stand. But what if we could bypass human error and ask the atoms themselves? Because deep within the atomic architecture of matter, every substance carries an unforgeable fingerprint. The atomic architecture of matter just never lies. Section 1. The ultimate forensic detective. So where other investigative methods might just give you some helpful clues, the GCMS, gas chromatography, mass spectrometry, turns mysterious chemical mixtures into undeniable mathematical certainty. And you know, it's actually amazing to think this modern marvel is a historical marriage of two revolutionary breakthroughs that were born half a century apart. Back in 1900, a Russian botanist named Mykola Tsvet invented chromatography to separate plant pigments. Then, decades later, J.J. Thomson and Francis Aston figured out how to weigh the unseen, building mass spectrographs to measure atoms by their mass-to-charge ratios. But the real game changer? That happened in 1955 when Roland Golke and Fred McLafferty combined the two. They created a single instrument capable of finding one targeted molecule hiding inside a mixture of millions. To truly wrap our heads around how this works, we have to shrink way down and step completely out of our macroscopic world. For this explainer, our protagonist is a single methamphetamine molecule. It's a highly precise combination of exactly 10 carbon, 15 hydrogen, and 1 nitrogen atom, which gives it a molecular weight of 149.23 grams per mole. We are going to follow this single microscopic entity on what is basically a treacherous micro-odyssey. Phase 1. The separation. Okay, the crucial point here is how this journey begins. Our molecule is violently ripped from its liquid bonds, injected into a port heated to a scorching 250 degrees Celsius. In mere milliseconds, the liquid solvent it was trapped in just vaporizes instantly. Now, inside this glass liner, the system has to make a harsh decision. It operates in what's called split mode. That means up to 99% of that vaporized cloud is immediately vented right out of the machine. Why? Because if it wasn't, this highly sensitive instrument would literally be blinded by the overload. Our surviving molecule is then pushed forward by an inert, high-purity helium wind, which carries it straight into the heart of the chromatograph. Welcome to the GC column. This is, literally, a molecular marathon. Imagine 30 meters of microscopic tubing all tightly coiled up inside an oven. The inner walls of this massive, microscopic labyrinth are lined with a nonpolar stationary phase. As our molecule enters, the oven temperature steadily ramps up from a warm 60 degrees Celsius to a blistering 300 degrees Celsius. This right here is where the actual separation goes down. The lighter, more volatile adulterants that might be mixed in with the drug, they just sprint ahead through the column. Meanwhile, the heavier or more polar compounds are going to cling tightly to that liquid stationary phase coating the walls, lagging way behind. Our methamphetamine molecule continually bumps into this liquid phase, dissolving for a split second before vaporizing back into the gas stream. Its speed is entirely dictated by its own unique boiling point and chemical affinity. This exact, highly specific time it takes to traverse the 30-meter labyrinth is called its retention time. And this is absolutely crucial, because this retention time is the very first piece of solid evidence in proving exactly what the substance is. Phase 2, the shattering. Now, what's really interesting about this next phase is the extreme, violent environment waiting at the very end of that column. Leaving the column, our newly isolated molecule plunges into the electron ionization chamber, and this place is a true deep vacuum void. We are talking about a pressure drop of a billion-fold compared to normal air. The machine does this because it has to guarantee our molecule doesn't accidentally smash into any stray oxygen or nitrogen molecules from the air, which would completely ruin the analysis. Once inside, it enters a literal firing range. A tungsten filament acts like a microscopic gun, bombarding our molecule with exactly 70 electron volts of energy. That number, 70 eV, is incredibly important. It's a precise, standard energy level calibrated in forensic labs worldwide. That standard ensures that a test run in New York will perfectly match the results of a test run in Tokyo. The impact from this electron beam is intense. It literally rips away one of the molecule's own electrons. This instantly turns our previously neutral protagonist into a positively charged, highly unstable molecular ion. Now, holding this massive excess of 70 eV energy, the molecule just cannot hold itself together. The chemical bonds snap violently along highly predictable fault lines, breaking into distinct structural fragments. These newly charged, shattered fragments are then shot directly into the quadrupole mass filter. Think of this as the ultimate electric sorting hat. It's made of 4 perfectly parallel metal rods that rapidly ramp up radiofrequency and direct current voltages. By fluctuating these fields, it creates a wildly unstable path. Most of the wobbling ions crash into the metal rods and are neutralized. At any given microsecond, only fragments with a very specific, stable mass-to-charge ratio can successfully fly straight down the center. So once a sorted ion successfully navigates those rods, it hits the primary conversion dynode. This single impact sparks an incredible exponential cascade of electrons. By the end of this multiplier process, one single microscopic atomic impact is transformed into a readable electrical pulse of over 1 million electrons. It's wild. The machine has successfully turned an invisible, singular atomic event into a massive, readable electrical current. Section 4. Decoding the molecular fingerprint. Okay, so the machine has done all its chaotic work, and now we have to translate those electronic cascades into unquestionable data. The computer generates 2 definitive graphs. First up is the total ion chromatogram. You can think of this as the when. It's a time map showing exactly when compounds emerged, looking like a series of peaks. Maybe there's a huge spike at exactly 8:42 minutes. When the analyst clicks on that specific peak, the software brings up the second graph, the mass spectrum. This is the what. It's the structural fingerprint of the shattered molecule, plotting the mass-to-charge ratio of the fragments against how abundant they are. Let's put the clues together for methamphetamine. The chemist is going to look for specific markers on that mass spectrum. Because of the predictable way it shatters, the most stable fragment creates a massive, towering peak at a mass-to-charge ratio of 58. We call this the base peak. But if you look further down the chart, we also spot a smaller peak at 149. That right there is the intact molecular ion, basically the small fraction of molecules that somehow survived the electron bombardment without shattering at all. That 149 confirms the total original weight of the molecule. And molecules have to be thermally stable and volatile. Thermally fragile molecules or large biomolecules like proteins, they just break down in that 250-degree injection port. Even certain synthetic opioids, like various fentanyl analogs, can degrade in the hot inlet before they even reach the column. To get around this, analysts are forced to either use chemical derivatization to protect the molecule or bypass GCMS entirely and use liquid chromatography tandem mass spectroscopy, which runs comfortably at room temperature. Section 5. The future of forensics. So, let's look ahead to see how the science of justice is rapidly evolving. The next frontier brings ultra-high resolution into the mix. We're talking about technologies like Orbitrap mass analyzers that can measure fragment masses out to 4 decimal places. That easily distinguishes between totally different chemical compounds that just happen to share identical nominal weights. And on top of that, engineering advances have given us palm-sized, field-portable GCMS units. This literally allows investigators to run lab-quality tests directly at the crime scene in a matter of minutes. Ultimately, the GCMS gives a voice to molecules that cannot speak for themselves. It acts as science's unbiased, precise, and absolute molecular witness. It bridges that gap from an anonymous speck of powder on a dark table to an unmistakable spectral pattern on a digital screen. Which leaves us with a pretty provocative thought to wrap up this explainer. If atoms are the ultimate, unquestionable witnesses that simply cannot lie, what happens to the speed and accuracy of criminal justice when this incredible mathematical certainty is no longer locked away in a state laboratory? What happens when the power to instantly decode the molecular universe fits right in the palm of every investigator's hand? Food for thought. Thanks for joining me on this deep dive today, and I'll see you in the next explainer.